Anionic compounds, if you remember, we said that substances are made up of two types of thing, or two types of particle. We have cations, which are the positive ions, those atoms that have lost electrons, and so as a result now have more protons and electrons and have a positive charge. And it's made up of anions, and so we gave the example of, say, sodium chloride, which we'll get to how we name that in a little bit. That's our focus moving forward here. But what we said is that this is an ionic substance, that it's actually not made of two neutral atoms that are put together, but rather a sodium ion that has a positive charge and a chlorine ion that has a negative charge. And this would be the formula unit of that they actually form these sort of vast sort of matrices of alternating positive sodium ions and negative chlorine ions. So what we want to talk about here is a little bit about how we know these substances form what they do, why this is NaCl and not Na2Cl or NaCl3. And so to do that, we're going to look at the idea of valence and of oxidation numbers. So we can indicate how many electrons an element has gained or lost in an ionic compound by indicating something that's called its valence or its oxidation number. These two are similarly related terms, but they're not exactly the same, though oftentimes we will use them similarly. So let's say that this sodium right here, so what we said is that sodium has a charge of positive, just +1. That means it's going to lose 1 electron. That chlorine has gained 1 electron, but not every cation is going to lose 1 electron. Some will lose 2 or 3. Not every anion is going to gain 1 electron. Some will lose 2. Some will gain 2 or 3 or 4 or 5, like that. So let's look at these two terms. So an element's valence is the number of electrons that atoms of that element have used in bonding. So for this sodium right here is that it has given away 1 electron, and so there's 1 electron involved in bonding. It would have a valence of 1. The chlorine has gained an electron to turn into an ion that's allowed it to bond here, and so it would also have a valence of 1. And so that's what an element's valence is, the number of electrons that atoms of that element have used in bonding. Now, an element's oxidation number, on the other hand, is the number of electrons gained or lost in forming a compound. The primary difference is that valences are always positive. They're just the number of electrons that are here. But when we talk about oxidation number, this isn't really a very clear way of saying it. We say number of electrons gained or lost. Basically, it's a positive or a negative number. If the atom forms a cation that it has lost electrons, then it'll have a positive oxidation number, and it'll have a negative oxidation number if the atom forms an anion, that it's gained electrons. So it is sort of backwards than what you'd expect. It'll have an oxidation number of +1 if it's lost 1 electron. It would have an oxidation number of -2 if it's gained 2 electrons. But that's sort of how it works, is that the oxidation number is the number that it's of electrons that the atom has gained or lost in forming that compound, whereas the valence is simply how many electrons are involved total. In both these two cases, the first one would be a valence of 1, the second one would be a valence of 2, but an oxidation number of +1 and -2. So we sort of gave some examples of oxidation numbers. So an element that loses 2 electrons in a compound would have an oxidation number of +2. Since it lost 2 electrons, it has 2 more protons now and has a positive charge of 2 plus 2. An element that gains 3 electrons in a compound, an oxidation number of -3, because it's lost 3 electrons, or it's gained 3 electrons, has 3 more negatives than it does positive, so it's overall -3. If we have an element that does not lose or gain electrons, it has just the same number of protons, same number of electrons, oxidation number of 0. Okay? So if we look at the valence, this one right here would have a valence of 2 because there are 2 electrons involved in this compound, this element that lost its 2 electrons of the compound. This would have a valence of 3 because of the fact that it has 3 electrons it's gained that are involved in forming this compound. This would have a valence of 0 because there are no electrons being involved in this particular compound. In fact, this wouldn't form a compound at all. This would just be a lone element. Terminology-wise, I just want to throw this out. There is, we said, this difference between valence and oxidation state. Oftentimes they're used informally as synonyms. So sometimes that we're going to be talking mostly about these oxidation numbers. Sometimes you'll hear me, to shorten things up, I'll refer to this as the valence. I'll say, what's the valence of this element? In normal usage, we're going to use that to sort of mean oxidation number, though to be technical, there is that difference. Valence is the number of electrons involved. Oxidation number is positive or negative, tells you whether it's lost or gained. All right, so let's look at some rules about finding these oxidation numbers. So number one, neutral atoms that are not in compounds have a valence of 0. So if I just had a sodium atom right here, not involved in sodium chloride, just a sodium atom sitting by itself, it hasn't gained electrons, it hasn't lost electrons, it is a neutral atom, it'll have a valence of 0, it'll have an oxidation state of 0, or an oxidation number of 0. Number two, single ions that are not in compounds, but they are ions. They're not neutral like this guy is. They are ions. They're not in compounds. They have an oxidation number that's equal to their ionic charge. So here we have F with a little minus, if you can see that right there. Remember that minus indicates that it's -1 is its ionic charge. And so since its ionic charge is -1, its oxidation number is -1. We have vanadium +3 right here. Since it's got an ion that's by itself in this case, it's not involved in another compound. You don't see any other elements that are attached to this out here. That means it's a single ion by itself. Its ionization number, or its oxidation number, is going to be equal to what charge it has as an ion. That's +3, so its oxidation number is +3. Na plus, positive charge, +1, oxidation number +1. Now, that covers things that are by themselves, both neutral atoms and ions that are by themselves. But atoms that are in compounds tend to have predictable oxidation numbers, so they're not random. Na, we said in the first case, when it's with chlorine, the Na is going to have a plus charge. It'll have an oxidation number of +1. That's not random. Na will only have an oxidation number of +1, except in some very rare circumstances we're not going to run into. It's predictable. Now, how do we predict it? Well, it's based on the organization of the electrons in the electron cloud. We'll get into that in a lot more depth in a future unit here. And it's based on how attractive the atom is to its own and outside electrons. And so we'll cover why it is later. But right now, you just need to know that it is predictable. So here's how we're going to go with this. So the reason why this is important is that in compounds, the total oxidation number of all the atoms combined is 0. We can use this fact to determine the chemical formula of the compound. So back to our sodium chloride. We said the Na, the sodium, has an oxidation number of +1. The chlorine has an oxidation number of -1. Well, I have NaCl, one sodium, one chlorine. So 1 times +1 is +1. 1 times -1 is -1. If I add those two up, +1 plus -1, I get 0. Because of the fact that the total oxidation number of all the atoms in the compound is 0. We can use this to figure some things out. We'll take a look at an example of that. Now, this is true even if the compound is covalently bonded. So we've been dealing with these ionic bonds here, ionic compounds, but all these rules about oxidation numbers are also true in covalent compounds, even though in covalent compounds the atoms don't completely ionize. So if I had CO2, which we'll look at in a second, right here, in this particular case, the carbon has an oxidation number of +4. Each oxygen has an oxidation number of -2. This is covalently bonded because carbon is a non-metal as the cation that's out here. Since I have 2 -2s, gives me a total of -4. Since I have only one carbon, that's 1 times +4, +4 plus -4 equals 0. So my rule still stands that the total oxidation number is 0 even in covalently bonded compounds. That'll let us figure things out. Let us figure out what the number of each atom is in both covalently bonded compounds and ionically bonded compounds. So looking at finding these oxidation numbers, here's some rules. And for the most part, these rules are in order. The most important rules are on top, and we're going to go to less important rules as we move down. So first rule, fluorine has an oxidation number of -1 in all compounds. That's always true. Okay? Number 2, hydrogen has an oxidation number of +1 in compounds in general, unless it's combined with a metal. In that case, it's -1. So if I had hydrogen and fluorine, we said that fluorine has an oxidation number of -1, so that's going to be -1 for fluorine for the oxidation number. Hydrogen has it says an oxidation number of +1 in compounds, normally, unless it's with a metal. Well, fluorine's not a metal. So that means hydrogen is +1, and so to get this to balance out, we have 1 hydrogen and 1 fluorine because +1 plus -1 is 0. That balances out. We have a neutral compound here. Now, next rule here. Well, actually, for hydrogen here, the other possibility would be something where I did have it with a metal, Na and H, like this. Sodium, we said, is +1. Hydrogen has to be -1 to make those overall valences balance out. And so we end up with a neutral atom. So that's how hydrogen works. It's +1 is its oxidation number, its valence, whenever it's in a compound, unless it's combined with a metal, in which case hydrogen has an oxidation number of -1. Next one up, oxygen. Oxygen only has an oxidation number of -2. The only exception is that if oxygen is with fluorine, because of the fact the fluorine rule is first, fluorine has to be -1, and so if fluorine's -1, that means oxygen would have to have a positive valence in that case. That's really not going to happen that often. I'll show you later on how you would deal with that if you did come up. But normally, oxygen is going to be -2. Now, we're not going to go through every single element the way we have these three. These are the three important ones that sort of we want to know right off the bat right here. For all other elements, or for most other elements, at least those that are in the main group of the periodic table, is that an element's column number, or its group, the group is the technical term for this, on the periodic table often determines its oxidation number. We have a table down the bottom that shows this. So elements that are in group 1 have an oxidation number of +1. Elements in group 2 are typically +2. Elements in group 13, +3. Elements in group 14 are either +2 or +4. They could be either one. Group 15, -3. Group 16, -2. Group 17, -1. So let's show you where these groups are. So group-wise, we see our group numbers are going across here. So group 1 are these elements right here. And so that's group 1. So group 1, we said, typically has an oxidation number of +1. That works out pretty well. Look at that. There's hydrogen right there. We said normally hydrogen is going to have an oxidation number of +1 unless it's with a metal. And then down here we have sodium. Hey, we've been seeing sodium. We've said it has an oxidation number of +1. That's because it's in group 1. Group 2, we said has an oxidation number typically of +2 right there. The next one we said was group 13. That's way over here. Group 13 is typically going to have an oxidation number of +3. Group 14 right here we said is either going to be +2 or +4. We'll get into why that is later on, but for right now that's what you just need to know, is that they could be either one, but those are the two common ones here. Group 15 we said is typically going to be -3. Group 16 is going to be -2. In fact, there's oxygen. We already said that was -2. That was one of our early rules. Group 17 right here we said is going to be -1. Now group 18 we didn't talk about, but there's a good reason for it. These elements right here are known as the noble gases. They do not react with anything for the most part. And because they don't react with anything, they don't form compounds, they don't share electrons, they have an oxidation number of 0 right there. And so that's sort of our oxidation number general rules. But notice that we've sort of skipped a very large number of elements in the periodic table. This whole giant group right in here, well not group, but this whole collection of elements here. So what do we do if we need to find out what the oxidation numbers are for those guys, what their valences are? Well, we're going to have to look to the periodic table. And so for special cases, and also for cases where some of these guys, the non-metals that go off through here, when they are cations, then we're going to need to do this as well. But for special cases, we'll need to look at a periodic table to determine the oxidation number. Most periodic tables, you'll see a key somewhere on it, and I've sort of zoomed in on just a section of the periodic table here. And notice on this one, maybe hard to read, but it says oxidation states, OX states on here. Those are your oxidation numbers, and so we can see those right here for hydrogen. See, +1 and -1. Because as we said, hydrogen is normally +1, except when it's the metal, then it's -1. So it gives you both possibilities for hydrogen. This is group 1, and so all this is group 1 going down and then farther off here, and notice what they typically are, +1, +1, +1. Here's group 2. We said those should all be +2, and you can see +2, +2, +2. But then we get to these that are out here that aren't part of any group. And so to figure those out, we have to look down here. So for scandium, its most common oxidation state, most common valence is +3. Titanium, though, has 3 different possibilities. It could be +2, could be +3, could be +4. Vanadium has even more. It could be +2, +3, +4, +5. Chromium could be +2, +3, or +6. But we would not expect chromium to be +1 or +5 or -7. It's only going to be one of those 3 in the vast majority of cases. And so what it tells you on the periodic table, for those that don't fit the normal oxidation number rules, it'll tell you exactly what the oxidation number should be. So let's look at this, how we use oxidation numbers to figure out what the chemical formula is. So as we said, total oxidation number of all the atoms in a compound is 0. So let's look at H and O. So hydrogen is, we said, +1 or -1, depending on if it's with a metal. Oxygen is definitely not a metal, so that means hydrogen is going to be +1. Oxygen, we said, was -2. Even if you didn't know that about hydrogen, the fact that oxygen has to be -2 is going to make hydrogen be +1. So the question is, how many hydrogens and how many oxygens do I need to make the total oxidation number of the compound 0? Well, I would have to have 2 +1s and 1 -2, because if I had 2 times +1, and I added that to 1 times -2, then I would get 2 plus -2, and that would equal 0. So I have to have, for this formula, 2 hydrogens and 1 oxygen, which gives me H2O, our good old friend water right there. That's one of the reasons why it has to be H2O. Let's take one that you don't know, aluminum and oxygen. This would be a compound called alumina. And so for this, we'd have to look at the aluminum first. We say, okay, well, where is aluminum? So let's go back to our periodic table. Aluminum is right here. So aluminum is in group 13. We said group 13 is typically going to have an oxidation state of +3. And so for +3, that's going to be our aluminum. I usually like to write it up top. Oxygen, we said, was -2. And so we've got to find how many aluminums and how many oxygens are needed to make these valences balance out so that I end up with 0 total oxidation state. So 3 and 2 don't fit into each other, but the least common multiple is 6. So for least common multiple 6, I'd have to have 2 aluminums right here. And to get to 6 for the oxygens, I'd have to have 3 of those. And so my formula would be Al2O3 for that compound. Let's try another one, C and S. So I have carbon and I have sulfur right here. And so let's take a look at it. Carbon, going back here, is right in here. It's in column 14. Ooh, that one's a little harder. It said it has 2 possibilities. Could be +2 or could be +4. And so right now we don't know which one it is. We need something to tell us which one this is for this carbon here. Now sulfur, on the other hand, is going to be in, let's see, sulfur is right here. That's in group 16. It's -2 is going to be its oxidation number, so -2 for that one. And so there are 2 possibilities for this compound. So it's not just one possible compound you could have of carbon and sulfur. So one possibility is, let's look at this if we use the +2. And so if it's +2, then the carbon's +2, the sulfur's -2. We just need one of each, so it's just going to be CS. So that's our first possibility. The second possibility is the carbon is going to be +4. If the carbon's +4, then I have to have 2 sulfurs to make that to work. And so I would have my carbon is +4 total, my sulfur is going to be -2 times 2, which gives me -4, and then that would balance out. So there are 2 possible compounds of carbon and sulfur, CS and CS2. Now, this is a little bit of an issue because we're going to need to figure out a way to name these, because the rule is that you can't have one name for 2 different compounds. So CS and CS2 will have to have 2 different names. But for right now, all we need to know is that if you have 2 possible oxidation states, that implies there are 2 possible compounds of these 2 elements. If there were 3 oxidation states for carbon that were possible, that would mean there are 3 possible compounds. But that's sort of how you'd figure out what it is. Right now, we don't know how to determine which one of these is the correct one and which one of these is the incorrect one. In fact, right now, there's not enough information to figure that out, but we'll figure out how to do that later. We'll see a way to know which one is which. Next thing we want to look at is naming monatomic ions. So whenever we name a compound that's made of single ions, and we say single ions, we mean no polyatomic ions. So we could have the situation where we had the NaCl because we have a sodium ion and a chlorine ion. We would not use a situation where we had a polyatomic ion. So you could not have something. This would not necessarily work if we had, let's say, NaOH, where the OH is the anion and the sodium is the cation right here. So for right now, we're not going to deal with naming these. We'll name those later. So here's the rule. So first thing, as we've seen before, cation first, then anion. So if I had oxygen and hydrogen, we said oxygen is going to have an oxidation state of -2, hydrogen +1. This tells us the H has to go first, the O has to go second, and then balancing it, I'll give us 2 right here. All right, so it has to be H2O. You can't say it's OH2. That's not correct because cation goes first, anion goes second. Even in a case of a covalently bonded one, you look at what the oxidation numbers are. They'll tell you which one is going to be the cation, which one's going to be the anion, even if they're not technically cations and anions. So next thing. If the cation has only one common valence or oxidation number, the first part of the name is simply the name of the cation's element. And so water is sort of an exception here. It uses a common name, not a chemical name, but let's take a look at the one we had right here, NaCl. All right, so Na is sodium. Sodium has, if you look at your periodic table or you look at, you can see that it's in group 1. Group 1 has a +1 oxidation state, and so it's going to be first. And it says that since that's only one possibility, the first part of the name is the name of the cation's element. So it would just be sodium. So sodium is the first part of the name if I'm trying to name this guy right here. Okay? The anion portion, if the anion portion has only one common valence or oxidation number, the ending of that element is dropped and replaced with "ide." And this is true for these monatomic ions, anions, ones where it's not polyatomic, as we said, it's not that guy. It's just one element. And so in this case, our anion is Cl, chlorine, and so what we're going to do is we'll say chlorine is what we would say, I-N-E, but we want to drop the ending of that name and replace it with "ide," and so we are going to get rid of the "ene" and add I-D-E, and so this becomes sodium chloride would be our name here. So cation first, then anions, first rule. If the cation only has one possible valence or oxidation number, the first part of the name is the name of the metal, the name of the cation's element, which is just sodium in this case. If the anion has only one common valence or oxidation number, the ending of the element name is dropped and replaced with "ide." That IDE tells you it's a single element, monatomic, in the vast majority of cases.
So let's try this out with a few of them. We have sodium chloride. And so the first bit of doing this is going to be saying, okay, we have sodium. So looking for sodium on here that's Na. We have that right there. Chloride, the key part in looking at this is recognizing it has that IDE. And so we're looking for the element that starts chlor, and that's going to be chlorine. And so we look for chlorine, and chlorine is over there on the right side. And so chlorine, I'll make it a different color just so we can remember what we got here. Now to work this out, we've got to make sure that the ionic charges are balanced. So we look at sodium. Sodium has a charge of +1. And so we got +1 for sodium. Chlorine, on the other hand, says it is +1, +5, +7, -1. Now, if it were +1, +5, or +7, there's no way these could balance. You can't add up two positive numbers and end up with 0. You wouldn't have a neutral one. The chlorine has to be, in this case, the -1, and that sort of makes sense because, you know, it ends in "ide." It has to be an anion. And so, by definition, it has to be the -1, and turns out chlorine's most common valence is going to be -1. So, in this case, NaCl, +1 plus -1, that equals 0. These are balanced. So our overall, we're already where we want to be. We've got the formula here. So we've got our total one, just NaCl. And that's it. All right. So our next one, aluminum sulfide. So our cation here is going to be just aluminum. That one's pretty straightforward. Now the next one is sulfide. It does end in IDE, so that tells you that's an anion, as well as the fact that since aluminum is positive, it's going to have to be an anion. So we look up sulfur. Sulfur is +4, +6, -2. And so in this case it has to be -2. Whereas aluminum, if you look it up, is only one thing. It's only +3. And so we only have +3 for that. And so the question is, how do we get these to balance out? Because unlike the sodium chloride we saw before, 3 and 2 do not add up to be 0. And so to do this, what you want to do is you want to look for the least common multiple. And so what number, it will both evenly divide 3 and 2. And so least common multiple between 3 and 2 is just going to be 6. And so how many aluminums do I need to have a total of +6 if each one is +3? I need 2 of them. Because 2 aluminums times the +3 gives me a total of +6. For the sulfurs, each one is -2. That means to get a total of -6, I have to have 3 of those. And so my overall formula for aluminum sulfide is Al2S3, like that. And so that's how you'd work that out. All right, on to our next one, calcium bromide. First thing we look up is calcium. It is on the front because it says that normally is the rule, or always the rule is that cations are going to come front and then anions are on the back side of any written out formula. So we have calcium bromide. The first one here is calcium, Ca. If we look at the charge on calcium, it says it's +2. So +2 is the charge on calcium. The next one is bromide, ends in IDE, and so since it ends in IDE, that tells us it's the anion. And so bromide would be bromine. So we put bromine down here. Bromine is +1, +5, -1, but it has to be the negative. So -1. These numbers do not match up to start with, but we say what's the least common multiple between 1 and 2? What do they both go into evenly? Well, we'd have 1 calcium, and we would have to have 2 bromines. And so I have to have 2 bromines right like that. So our final one is going to be CaBr2, like that, because 2 bromines, 2 times -1 is -2, plus +2 is 0, so that works out for that one. Our last example here is carbon nitride. So for carbon nitride, the first one is carbon, and so we'll write out the cation as carbon. Carbon, if we look at it, is +2, +4, -4. So there are 2 possibilities. It could be +2 or it could be +4. Now, whenever you've got a case like this, is that for writing these out, is that technically is that this carbon, there should have been something to indicate what valence that carbon has. Probably it would be in between this. We'll talk about that in just a second. Since it's not here, what we're actually going to find is that the most common valence state for carbon would be 4, would be +4, because if you look at it, it's got 4 valence electrons. And so that means it could lose 4. If it only lost 2, that wouldn't be as common because it would have to, it would still have a couple in its valence shell, but it wouldn't have gotten rid of all of them. So this is going to be carbon 4, and so that's +4. Now the other piece here is nitride, and so nitride, drop the IDE, nitrogen would be that. And of course, nitrogen is our other one that is most uncommon here. If you look at it, it's +or-1, +or-2, +or-3, +4, +5. So this could be -1, -2, or -3 for its charge. Taking a look at nitrogen, though, you can see that it would have to gain how many electrons to get a full set of valence electrons to get to 8. So it would have to gain 3 more. So nitrogen is one you just sort of have to remember. When it's negative, is almost always going to be -3. And so you just sort of have to remember that and memorize it. So unless you're told otherwise, nitrogen is going to have a charge of -3 when it's an anion. So we've got these two right here. We got 4 and 3. Least common multiple here is 12, and so 3 times 4 gives you that one right there. 4 times 3 gives you 12 right there. So those two would cancel, and so our final compound is C3N4 for carbon nitride.